University in Australia, and he will speak on the Schrödinger propagator for scattering matrix.
Thank you. I'd like to thank the organisers of this meeting for inviting me to speak here. I'm describing joint work with Jared Wunsch, who's at Northwestern University, and there's a paper on the archive at this address. So we're interested in the Schroedinger, time-dependent Schrödinger equation, which is this equation here, 1 over I dt plus 1/2 Laplacian psi equals 0. So psi is a function of space and time. We give an initial data at t equals 0, and we'll be looking at this on curved space typically. So the Laplacian is grad. We're going to use the positive Laplacian here. So this has a well-known fundamental solution in Rn, which is given by this kernel. And from this kernel, we can see the essential features of the propagator. This fundamental solution is called the propagator. For one thing, it has infinite speed of propagation. So this propagator formally has a limit delta of w minus x at t equals 0, and instantly it's non-zero everywhere. In that sense, it's like the heat kernel, and indeed this is quite evidently just the analytic continuation of heat kernel in time. But unlike the heat kernel, there's no Gaussian decay. This kernel does not decay at all as you move away from the source of the singularity. And that's a reflection of unitarity. This kernel is the kernel of e to the I t Laplace, or e to the minus t Laplacian over 2. And nothing can disappear because by unitarity you can get back to where you came from by applying the adjoint operator. The other feature of this is, curious feature of this kernel, is that singularities can instantly appear and disappear, or apparently anyway. So, by the way, this little u should be a capital U. This is meant to be the same as this one. This has the formal limit in distributions. T equals 0, the delta function, while as soon as t is positive, this is a smooth kernel. So the delta singularity apparently disappears instantly. And similarly, if you take as initial data, say this kernel at some negative time and evolve it, well, you'll get a delta function appearing. So singularities can also appear instantly. However, bearing in mind what was said about unitarity, the singularities should not really be thought of as disappearing and appearing, but rather moving somewhere. And where they're moving to must be at infinity. So somehow the interior singularity is being changed into oscillatory behavior at infinity, and this can revert back to an interior singularity. So I'd just like to review next some previous work on the propagator and propagation of singularities under the Schroedinger equation. First of all, there's Kapitansky and Safarov showed that if you start with initial data, compactly supported distribution, then that always instantly becomes smooth. I should say this is, of course, in for curved metrics now. This is immediate for the flat metric by this propagator. And in later paper, they obtained a parametrics modulo C infinity, but without control at infinity, or without expansions at infinity. Craig, Kapler, Strauss obtained a theorem in which they obtained regularity of a solution actually, this description is not accurate. Scrap that. out. In a diagram, what they showed was that if you have, so this is in, say, in Rn with some metric perturbation, that if you have regularity of the initial data in some cone, this is going out to infinity, if the initial data is irregular here, then for all times you get regularity of the solution along geodesics whose final direction is within this cone. So that means microlocally all of these directions are not in the wavefront set of the solution for positive time, and these ones are not in the wavefront set of the solution for negative time. So that was a curious sort of result where they had localization in direction, but no localization in either space or time. So for any point here, there's a geodesic with this as final direction. So there's no localization in x or t, but localization in the psi variable for the wavefront set of the solution. This was improved by Wunsch in '98 in his thesis, where he showed that, he improved this to localization in t, but not in x. And that was described in terms of a so-called quadratic scattering wavefront set of psi 0, which measures quadratic oscillations at infinity. Quadratic oscillations referring to this quadratic phase function here. And I'd like to mention a couple of other results, a few other results on the Schrödinger equation. Robbiano and Zuili obtained the analog of Wunsch's result in the analytic category, so for analytic wavefront set and so on. There are Strickhart's estimates, which are LP-LQ spacetime estimates on the solution of the Schrödinger equation in terms of a norm on the initial data, have been obtained by Burke, Girard, and Svetkov, and also by Stefanani and Tataru. And in the case of the Schrödinger equation where we have the flat metric on Rn but a potential perturbation, there have been various accurate parametric constructions. A number of those going back more than 20 years. So we're interested in not potential perturbations but metric perturbations. We want to study the Schrödinger equation in the variable coefficient case and understand, two things which are closely related: the form of the propagator, in particular the asymptotic expansion, the oscillations at infinity, and as a corollary, we'll find information about the propagation of singularities. So the results I've described have had a partial understanding of propagation of singularities for the Schrödinger equation. Just contrast that with the highly satisfactory theory of the wave equation, which I'm sure everyone in this audience knows very well. So if you consider the wave equation, which I've written in this form, dt plus I squared Laplacian u equals 0, and so look at the unitary group corresponding to that, then it's well known that this is a Fourier integral operator which quantizes the contact geodesic flow at time t. So if we denote by capital phi t the geodesic flow on the sphere bundle of our manifold X at time t, e to the it root Laplacian is an FIO quantizes phi t. And as a consequence of wavefront set mapping properties of FIOs, we get a nice statement about the wavefront set, that a point is in the wavefront set of the initial data if and only if it's in the image of that under geodesic flow at time t is in the image of the solution at time t. If and only if comes from unitarity, so that we can apply e to the minus it root Laplacian and get the other inclusion. So this is the sort of satisfactory statement that we want to make for the propagation for the Schrödinger equation. So these are the specific questions. I've more or less stated them already, but more explicitly. When and where can singularities appear in the solution at time t in terms of the initial data? Where do the singularities of the initial data go? That's essentially the same question. And thirdly, what is the structure of the fundamental solution of the Schrödinger equation? So a strong enough answer to 3 will automatically answer 1 and 2 in the same way that if we know point 1 of this theorem, then we get point 2 as a corollary. So what's our geometric setup? Well, we want to work on a Riemannian manifold, complete Riemannian manifold, with ends that look like the large ends of a cone. So, in other words, we have a metric which takes this form as we go out to the ends. So by the ends, I really mean r is going to infinity. And we have a metric that looks like this. This is a scattering metric as defined by Melrose. And actually, this is a slightly more special form, but this is any scattering metric can be put in this form by change of variables. So this is general. OK, so if h did not depend on r at all, this would be a conic metric. This would be an exact cone. And we're allowing this to be only asymptotically conic, so that h depends smoothly on r inverse. But if you like, think of the case where h does not depend on r. So this, in particular, we're going to think of this example. OK, so Euclidean space is evidently an example of this because Euclidean space is a cone. And any compactly supported metric perturbation of Euclidean space looks like one of these. Now, I want to think of this as a key example. And in fact, this is somewhat more general than this in the sense that we have this dr squared over r term, which is not allowed here. But our methods can deal with metrics like this on Rn. The reason why we want to include such terms is you get this is the mass term in an asymptotically flat manifold in general relativity. And when we, so Jared was talking to Yao about this, and Yao was not interested in our result unless we could do these sort of metrics. So emphasize that we can do that. And, the most crucial assumption is the non-trapping assumption. So we assume that our metric is non-trapping. Every geodesic reaches infinity in both directions. In fact, we can deal with the more general situation if we restrict our initial data to have wavefront set in the non-trapping region of phase space. So we'll get a microlocal result. Okay, so our Hamiltonian is going to be one of these Laplacian with respect to one of these metrics, plus, and will allow a potential, a rather mild potential, which has an asymptotic expansion in powers of 1 over r, starting with a term like c over r. C is a constant, and then the rest of the expansion. So we can deal both with Einsteinian gravity and Newtonian gravity. This is a Newtonian gravity term. All right, and we're interested in the Schrödinger equation for this Hamiltonian. We want to construct a parametrics for the fundamental solution. Sure, yeah. So all these coefficients should be smooth. Okay, v is a smooth function, and it Okay, so actually, let me... There's a smooth function of theta and 1 over r. So in particular, all the coefficients v minus 2, v minus 3, and so on are smooth. So we're working with... This is a big regularity assumption, v. We're not interested in low regularity theory here. Okay, so to get an idea of how we should go about constructing a parametrics, let's go back to the Euclidean fundamental solution for a minute, for the free Laplacian. And if we look at what this looks like when we fix x, say, and let w tend to infinity, so let r be the normal, the modulus of w, theta is the spherical variable, then we can write the kernel fixing x in this form, where we get a quadratic oscillatory term, e to the I r squared over 2t, and then we have a linear oscillatory term, e to the minus I r x dot theta over t, and then a term which is just some constant over t, x squared over 2t. So what we can see from that is that the quadratic oscillatory term is explicit. It's e to the I r squared over 2t. It's independent of x. Whereas the linearly oscillatory term is e to the I r x dot theta. That tells us what x is. That determines x. So that. And the final point about this is that the time t appears in the phase in a very simple way. It's just some function over t. So those are the essential features of the Euclidean propagator. So now we have a bit of a jump to the theorem statement. What's our result? Well, what we do is we divide the propagator by e to the r squared over 2t and look for the remainder, which we suppose, or which we hope at this point, to be simpler. And indeed, that turns out to be the case. If you write the propagator as e to the I r squared over 2t times something, so this is not very well written. This, here we're multiplying by a compactly supported function on the right, just that's simply saying that the x variable is restricted to lie in a compact set. That's all. We're restricting x to lie in some arbitrary compact set, and w is being sent to infinity, and we're looking at the asymptotics in that regime. We're not sending both variables to infinity here. So that's all. So now you know that. Let me get rid of the chi. Has this form, and the kernel of the quotient, Wt, is some sort of Legendrian distribution. It actually fits into the calculus of scattering fibered Legendrians that was in an earlier paper of mine with András Váci, and this is a slight generalization of the theory of Legendrian distributions, which was introduced by Melrose and Zworsky. So, well, it would be foolish to attempt to define these, but roughly the kernel Wt looks like a finite sum of terms of some sort of oscillatory form, where we have we do indeed have linear oscillations here. So we have some function phi times r over t. Phi is a smooth function of theta x, some additional variables v and r inverse, and then a is a smooth symbol. So I want to try to describe, this is not very illuminating, but I want to, in the rest of this talk, describe geometrically what this looks like and what it does. So at this point, I need to introduce the scattering wavefront set. since we're working on Rn, I can use this as a definition of the scattering wavefront set. It's simply essentially conjugated into the normal wavefront set by Fourier transform. This is normally a theorem. There's an intrinsic definition in terms of the scattering pseudo-differential calculus, but this will do for this talk. So the point of scattering wavefront set is to measure linear oscillation at infinity. For example, if you have this function e to the I alpha dot x, a plane wave in other words, which has linear oscillation at infinity, the scattering wavefront set is the set of points theta alpha, where alpha is the fixed constant there, and theta varies over the sphere at infinity. So the scattering wavefront set is a subset of the cotangent bundle of Rn restricted to the sphere at infinity. Okay. So another way of stating this theorem is that after dividing by the quadratic oscillations, the propagator is a scattering Fourier integral operator. It's an operator that exchanges normal wavefront set and scattering wavefront set. And since the Fourier transform also does that, an alternative way to state this theorem is that the Fourier transform composed with Wt is a Fourier integral operator, an FIO on Rn. Okay, so I want to say something now about the canonical relation of Wt. So, of course, this T star Rn at the sphere infinity is just the sphere cross Rn. That's all it is. And just exchanging coordinates gives us a diffeomorphism between this and the sphere bundle of Rn, and that induces a contact structure on this space, because there's a natural contact structure on that space. So what is the canonical relation of this Wt? It turns out to be the canonical relation of it turns out to be the graph of a function from this space to that space, which I want to describe now. It's this function capital phi. So given a point in the sphere bundle of Rn, which we think of as the initial condition of a geodesic, x xi hat, this means unit vector, we map it to the point theta, lambda theta plus mu. So theta is a direction, it's a point in the sphere, and this point in Rn we've just decomposed in components relative to theta. So mu is perpendicular to theta and lambda is parallel. And the definition, we can describe it explicitly as follows. Theta is the final direction of the geodesic that starts at this point, x xi hat. Lambda is the limit, as t goes to infinity, of t minus the distance from the origin of gamma of t. This turns out to converge. And that's a sort of sojourn time. This you can think of, so it's closely related to the sojourn time as introduced by Gilman. You can think of that as the time that the particle spends in the finite region of your manifold before shooting out to infinity. Of course, here, implicit in this is the non-traffic assumption, which says that every geodesic does reach infinity. Otherwise, this would not be well defined, and this map would not be defined, or at least not globally defined. And finally, mu measures the angle of approach to the sphere. So of all those geodesics that have that given final direction, mu is a coordinate on the set of those geodesics. So it turns out that this capital phi is a contact transformation, and the graph of phi is the canonical relation of this Wt. Well, except the this depends on t, and t turns out just through a scaling of the fiber variables in phi. So this will scale this variable by t inverse here. Okay, so in the special case that there's a unique geodesic, so if you look at x in Rn and a theta in the sphere at infinity, and if there's a unique geodesic that starts from x and has final direction theta, and if that's non-degenerate in terms of something having non-degenerate Hessian and so on, then locally the propagator will have this form, and that's actually not correct. It should be, this depends also on R inverse here, and this is the value R inverse equals 0, i.e. when you're at infinity. So locally, the propagator will have that form with no integral. So this is a nice WKB type expression of the simplest form when your Legendrian manifold is projectable, and if it's not projectable, you need the extra variables that we had in somewhere previously. Okay. And this, and the value of this, the phase, is the sojourn time. So the sojourn time parameterizes this when this is a graph. Okay, so let's just check that in the case of the Euclidean example. In this case, if we take this will give us the propagator at fixing x, and if we remove the quadratic oscillation, then we get this, and we see that we have a phase function x dot theta, and indeed that is the sojourn time in Rn, the flat metric. If we take, if we start at x, we take the geodesic, which has final direction theta, which is the geodesic x, t goes to x plus t theta, and we take this limit, we get minus x dot theta. So that agrees in the Euclidean case. So given that we've got a sort of FIO, which is associated to a canonical relation, which is a graph of a contact transformation, we should get an Egorov theorem, and indeed we do. It looks like this. Suppose we've got a properly supported zeroth order, well, that's irrelevant actually, pseudo-differential operator on Rn, and we conjugate it with Wt, then we end up with a scattering pseudo-differential operator. And the symbol of the scattering pseudo-differential operator at capital phi of Q is equal to the symbol of the original operator at Q. So that's really saying, that's justifying calling this an FIO. And finally, this gives us a nice propagation theorem for the Schrödinger equation, which looks like this. So given a solution of Schrödinger's equation, psi of t, which is e to the minus ith psi 0, the initial data, fix a t non-zero, then this point, this arbitrary point, is in the wavefront set at time t, if and only if this point is in the scattering wavefront set of the initial data multiplied by this quadratic thing. So, in other words, we can tell exactly when a point is in the wavefront set of the solution at time t in terms of the initial data. So, if you go back to what we had for the wave equation, this is some sort of analog for the Schrödinger equation. And the previous results are immediate consequences, sort of weakenings, effectively, of this theorem. So now I want to say some words about the proof, not too many. how do we construct the parametrics in slightly more detail? Well, we start with an ansatz for the propagator near. So think of x as being fixed. X is the location of our initial delta function. Then we start with an ansatz that looks like this for our propagator. And if you plug this in, it's a standard WKB type expansion. You find that the phase function psi here should be equal to the distance squared over 2. So that's perfectly reasonable. That's what happens for the Euclidean propagator. And this determines a Legendrian submanifold of this space. So here, I guess I should say I'm thinking of t as being positive or non-negative, and t equals 0 is a boundary. And so, in fact, so this Legendrian manifold lives at t equals 0. That's where the oscillations are happening. And the coordinates here are w and its dual coordinate zeta here, x and its dual coordinate psi here, and the coordinate dual to t, tor, there. So whenever you have an expression like this determines a Legendrian submanifold. Well, it's Legendrian in this setting. And this quite soon becomes a non-projectable Legendrian. In other words, we cannot parameterize it by the coordinates w and x because, a metric, given that we've made a perturbation of the flat metric, will soon get to a conjugate point, and at that point, this Legendrian tips up. So it becomes non-projectable, but remains perfectly smooth. When we parameterize it, we need extra variables corresponding to the rank of the projection. So we follow this Legendrian. We can parameterize it as long as we like, and we follow it right to infinity. The main point is to analyze the regularity of this Legendrian manifold as we get to infinity. So the Legendrian manifold has this expression, and from this we can see that zeta and psi are growing linearly in S, and tor is growing quadratically in S. So S is going to infinity. S is arc length along the geodesic. And R, which is the modulus of W, is asymptotic to S as S goes to infinity. So it makes sense, in view of those asymptotics, to introduce scaled variables. So as R goes to infinity, or alternatively as S goes to infinity, we introduce rho equals 1 over R and introduce these scaled variables, rho zeta, rho psi, and rho squared tor. And we also decompose zeta bar, which is rho zeta, into components relative to the direction, w hat. That was what I was calling theta before. So when you do that, you find that along every geodesic, these variables have some nice limits. With various numbers that come out. So in terms of these variables, the submanifold L, this Legendrian that we're following, that's swept out by these by characteristics, if you like, that start from the diagonal and go out in every direction. This submanifold L is bounded in terms of the scaling, in the sense that none of these variables are going to infinity as we go out to spatial infinity. But although it remains bounded, it's not smooth in these coordinates as you approach infinity. It turns out to have a conic singularity. But conic singularity is not so bad. It can be resolved by blowing up a certain set. So at rho equals 0, we need to blow up some of these points where which is the site of the conic singularity. So we blow up rho equals 0 these 2 points. And okay, so the picture is that what have I called these things? Nu bar. Somehow nu bar equals 1. Some manifold is coming down like this. This is the rho direction, and if we blow up that point, then we get a nicer picture. So by analysis of the Hamilton vector field, you can show that once you blow up, you've desingularized the manifold, the submanifold L. It meets the boundary transversely, and moreover, the boundary of this blown up space, so this new face introduced by blow up, actually turns out to be a copy of the scattering cotangent bundle, which is where this scattering wavefront set lies. So what happens is that if we start at any initial point for a geodesic, we can follow that bicharacteristic to infinity, and we end up somewhere here, and that is a point in the, or can be identified as a point in the scattering cotangent bundle. So this is actually the value, capital phi, of that initial point. So we've sort of determined this function capital phi in that way. It's somehow encodes the asymptotics of geodesic flow. And the symplectic nature of this construction implies immediately, it's standard, that capital phi is a contact transformation. And because of that, we can apply the theory of Legendre distributions on manifolds with corners. So one of the confusing things about the propagator is that we have oscillatory behavior as t goes to 0 and as we go to infinity, spatial infinity. So if we compactify spatial infinity, we've got a corner, we've got oscillatory behavior at both faces. So we need some sort of theory of that. So fortunately, András Vajsi and I had already done that for another problem. So we just had to use that. I mean, there was a ready-made symbol calculus for us. So that's what we used. And well, that's in some sense the end of the story, as far as I want to tell it, I guess. So what happens is, maybe I'll just draw one more picture. How shall I draw this? I usually think in these terms. So this face is t equals 0, and this face is r equals infinity. Or since we've introduced the variable 1 over r, which is rho equals 0. And we start with an initial point x, which is somewhere here. And we first determine the oscillations of the propagator as t goes to 0. And from that, we get this Legendre manifold. So we follow a bicharacteristic of the Legendre manifold, which of course that's in phase space, but I'll just draw it here, a diagram. And this eventually gets to spatial infinity, which is this face. And so we have one stage where we have to solve away the errors at t equals 0. So we get, in our propagator, we get an error which is order t to the infinity, but we don't get anything here. The construction only gives us t to the infinity and some fixed regularity at rho equals 0. And then there's a second stage where we need to solve away the errors at rho equals 0. And so part of the symbol calculus is that you can do that while maintaining your t to the infinity errors. So the next stage is error order t to the infinity, rho to the infinity. And once you have this, that's a good parametrics. You can correct that to the actual propagator. And the correction term is itself order t to the infinity, rho to the infinity. So that means you've determined the propagator. You've determined the oscillations both at t equals 0 and rho equals 0. Thank you.